Hey everyone, this is lesson 914 on transforming the absolute value function. So prior to this lesson, we talked about quadratics and graphing parabolas, giving you the graphing form of quadratic function. So here's a reminder of parts of the notes that I had given you last time. So in addition to quadratic function having standard form or factored form, we just finished talking about graphing form, also known as vertex form. So benefits of this form that we have here is just like the name says, vertex form. It specifically tells us where our graph, where our parabola is located. So locator point, more specifically our vertex, is going to be our h and k value, which is given to us in our graphing form. So then that's the nice part about this form. So we're going to be using this exact same form for the absolute value function in these notes. So this is why I'm reminding you about this one for quadratic function, because it's going to look very similar. So first thing we probably need to do is remind ourselves of what absolute value is. So absolute value, kind of short definition would be that it's the distance from zero. So if you think about it, anything you measure with distance is always going to be a positive number. So you would probably always say, I ran 5 miles. I drove 20 miles. So anytime you talk about how far someone's traveled, whether you're walking, driving, flying, every single time you're going to be talking about a positive number, right? We'll never say, I just walked -3 miles. Right? Even if you walk backwards, you're still going to say a positive distance. All right, so when we talk about distance from zero, zero meaning we're talking about a graph or number line, how far are we from that number zero? So we're always going to be a positive number. So in comparison to our quadratic function, right, they actually kind of behave very similarly. Quadratic function, which is x squared, anytime we put a number into this equation, it tends to always turn positive, right? So negative times a negative is always positive. So it's kind of almost the same idea with absolute value function. And in this case, we have absolute value bars on the side of the x. And this will always give us a positive number, right? Like we said, distance from zero. Except in this case, we're not going to be multiplying anything. So let's look at specific examples. So let's see. Here I have, let me show you these. All right, so here we have our two functions. Now, if I actually plug in, if I want to plug in the number 3 to our quadratic function, so this notation, this is the same thing as y. So just in case if anyone doesn't know. So this is the same as y equals to x squared. So this just tells us, lets us see what number we're going to be plugging in. So if I actually plug in a 3 to this equation, right, 3 squared, this is going to give us a 9, right? Now on the absolute value, we're going to be looking at when we plug in a 3, it's really asking us how far is 3 from the number 0, right? How many positions is it away? So this 3 represents us maybe traveling 3 miles or 3 feet. So this is going to be a 3. So you'll note the similarities and differences. They both ended up with a positive number, right? And with the x squared, that one actually changed value. Here it actually doesn't. we're not multiplying, it's not getting bigger. All right, so how does that change if we plug in a negative number? Well, similarly, we're going to plug in a negative 3 to our x squared. We're really plugging it into here. So x squared becomes negative 3 squared. So in this case, that's the same thing as negative 3 times negative 3. Right, so negative times a negative is positive, so that'll give us, again, a positive 9. All right, so you'll notice it didn't matter if we plugged in a positive or negative, we still ended up with a positive 9. So similarly with the absolute value function, if I plug in a negative 3, well, how far is negative 3 from 0? Well, that one is still going to be 3 units away. All right, so it doesn't get bigger. We're not multiplying by anything like we did with the x squared. We're just trying to determine how far is this number away from 0, right? Or whatever's inside the absolute value bars, whatever's inside, we want to figure out how far is it away from 0. In this case, the answer is 3. All right, so, all right, I guess that's all I have. I thought I had more. All right, so that's just in comparing both of those, that's what's happening with a quadratic function. That's how the absolute value function works. So just in case when we start to plug in numbers, you get an idea of like how to calculate y values when we plug in an x value. All right, so more specifically with the absolute value, some things we need to know. So here's the graphing form of the absolute value function. All right, so this is the absolute value function. And you should notice it looks very similar to the parabola function. It looks almost identical. The only difference on the quadratic function or the parabola, there was parentheses here and there was a squared. That was the only difference. So if I remove the squared and I leave absolute value bars, right? So this is not the number 1. It should be very obvious that those are straight lines that go up and down. Do your best to write those out. All right, so just like the graphing form of the parabola or quadratic function, this a value in front of the absolute value bars tells us two things. The orientation. So if it's a positive number, then that tells us it's going to be facing upward. And if it's a negative, then it's going to be facing downward. All right, so this is our positive orientation and this is our negative orientation, like we talked about with the quadratic. Stretch factor, it also does the same thing. So it'll get skinny, right? It'll get skinny or it'll get wide. So it's either stretched vertically or stretched horizontally. All right, so those are the two different stretches, just like the parabola. And locator points, in this case, we still get a locator point using the h and k value, which gives us our vertex. So that'll tell us exactly where either the top or the bottom of our graph will be. So I haven't mentioned it yet, but hopefully you notice that the graph of this, unlike the parabola looks more like a U-shaped. The absolute value looks more like a V-shaped. Right? So this is kind of the default graph. It looks like a V or an upside down V, or a skinny V or a wide V. Right? So that's really the two differences. These graphs are so similar. Almost everything, well, there's a lot of things they have in common. So that should make it a lot easier to graph these. If you know how to do quadratics, graphing quadratics, absolute value should be even easier. And if you struggle with quadratics, maybe this will help you understand how to graph quadratics. So hopefully by understanding both of these, it'll help strengthen your skills in graphing each of those. All right, so let's start with looking at the initial graph, because if we want to transform them, and we talk about transforming graphs, we're talking about either shifting it left or right, up and down, or maybe even making it skinny or wide. All right, so just like we did with quadratics, we want to look at what the default graph might look like. So here's the equation, y equals absolute value of x. And so you could plug in numbers, like like we did at the beginning of the notes. If I plug in numbers for x, if I plug in a -2, it's going to give me 2. If I plug in a -1, it's going to give me 1. Right? You'll notice all these y values from this equation end up being positive. So some things to notice, like I mentioned before, the graph is V-shaped. The locator point for this one is at 0, 0, right? So right at the origin, right? So there's your vertex. And right, so there's your vertex. And it's positive orientation, right? I've asked you a number of times, what's the orientation? Is it positive? Is it negative? Well, these are going in a positive direction. It's going in a positive direction. And the stretch factor in this case is 1. All right, so there is no a value that's seen, so there's like this invisible 1 that's in front. All right, so let's, yeah, I'll stop there. So that's the basics of it. Now everything after this is going to be transformations of this graph. So you already know all the graphs are going to really look like a V-shaped. So the only thing that's really going to change is possibly where it's located. The orientation might change, the stretch factor might change. But the one thing that never changes is really the shape of it. It's always going to look like a V. It might be skinny, it might be wide, it might be moved around, but it's still going to be V-shaped. All right, so let's look at this first example. In this one, I'm only focused on stretching this absolute value function. So I'm starting with something simple. So here's y equals to 2 times the absolute value of x. Now I've already set this up for us. The only thing left to do is to actually graph it. So I have a equals to 2. I want to identify all the parts because these are going to be helpful for us. So a equals to 2, that's our stretch factor, right? That's the number in front. H is equal to 0. Why is it equal to 0? Well, you'll notice there's actually nothing being added or subtracted to this x, right? Inside the absolute value bars, there's nothing in there. And then the k value is what's outside after the absolute value function. So there's nothing there, so that's 0 as well. So when you don't see anything, it's very simple, just an x, that means your h and k are going to be 0. Which means our vertex is going to be at 0, 0, right? Which is the 1 point that I've already plotted for us. All right, so the nice part about absolute value that I really like is there's a nice easy way to graph these without having to plug in numbers, right? That could be an issue for many people, or it just seems very tedious to have to plug in a lot of numbers. So the little trick that might help you is that the stretch factor is secretly the slope, right? There's not an official name, we don't really call it the slope, but it just so happens to be the slope of our graph. Now you notice this was V-shaped, so we're drawing straight lines. So since we have straight lines, linear lines, that means there's going to be a slope. And it just so happens to be related to our stretch factor. So the trick here is, since it's a stretch factor of 2, really means our slope is 2 over 1. So if you know anything about slope, this is really like our rise and our run, right? So starting from the vertex, I'm going to start at this point. Always start from the vertex, wherever the vertex is. It doesn't have to be the origin. It's wherever the vertex is. So I'm going to start from this point, and I'm going to go up 2, and I'm going to go over 1. All right, so up 2 and over 1 is going to give me this new point. And from this point, I could go up 2 and over 1. Rise 2 and run over 1. All right, so if you keep going, this will just give you a straight line, right? It'll give you a straight line. But that's only half of the absolute value function. So the nice part about this function, just like the parabola, right? If it was a parabola, we would have a line of symmetry. Well, what's nice is absolute value has the same. So you could, instead of just going up 2 and over 1 to the right, we could go up 2 and over 1 to the left. And that'll give us a point over here. And then up 2 and over 1 again to the left. So you should notice these points are equal distance from each other. All right, so there's one measurement of 1, measurement of 2. Right, so if we keep going, you should have, this will really go on forever. All right, so this creates our graph. All right, let's see if this works. Oh my God. I don't like this one. So this is going to be, I think I drew that wrong. Something like this. All right, here we have our graph. So you should notice it looks, if I compare it to the one above, you should notice this one looks skinnier. It looks more narrow because of that 2 that we put in front of it. All right, so you'll notice we really didn't have to calculate anything, and we were able to graph this very accurately. We have points, so all we really needed to know was where is the vertex located and how is it stretched. All right, so if this happened to be a -2, then this whole thing would be upside down instead. So since this is a positive, we already knew it was going to be facing up. All right, hopefully that made sense, and hopefully that helps when graphing these. All right, so 2 that I wanted to show you side by side was shifting left and shifting right, because I know a lot of people have had issues with this with the parabola. So since it's very similar with absolute value, I figured this would be a good time to spend more time on shifting left and right, which is really focused on our h value. So if I want to shift the graph left, as you can see, I already have the graphs here. So instead of it being centered at the origin, it's been moved, it's been shifted to the left 3 units. Now, why is it to the left? Why is our h value -3 when inside it says x plus 3? All right, so I've mentioned this, I kind of mentioned this before with the parabola. Your original equation, the original equation says y equals to a times x minus h plus k. All right, so you'll notice it already has a minus h. All right, so in order for us to keep that form, that has to be a -3. So if I actually rewrite this, I'm going to try to squeeze this in here. So this is actually the same thing as y equals to the absolute value of x minus -3 All right, so it's really a minus minus. So those that you remember, when you have two negatives or subtracting a negative, that becomes positive, which is why it looks like a +3. So when I ask you what's the h value, think about this. It was really this -3. That's where this -3 comes from. So when we look at shifting right, and there's already, it says minus there, so that must mean I'm focused only on the +3. All right, so here, that's a difference. So notice the notation here, or notice the sign, and notice how the h value is the opposite. Now in both of these, k value is 0, because there is no k given to us. The stretch value isn't anything else besides 1, so those are the default. So when we graph these, the graphs look identical, and literally I copied and pasted the same graph. The only thing that changed was this one on the left, shifting left, and then this one shifted to the right. Oops, I think I misplaced that. So I was going to make this, that's fine. Let's see if I could change this. It's supposed to be right here, just to make it a little bit more accurate. All right. Oops. All right. So shifting to the left 3, shifting to the right 3, or whatever number was there, that's going to tell you how much it's going to shift. Now the same idea works with shifting up and down, except we would be looking at the k value to help us do that. And so let's look at one example where we have a stretch factor and a shift. All right. So I'll zoom into this one. So I already have this set up for us, kind of like the other ones. We have y equals to 1/2 the absolute value of x minus 1. So nice thing to be able to do is identify the parts. So I always like to identify what my a value is, h and k, mainly because it's going to come in handy with more complicated problems. So here the h value is 0, you'll notice, because there's nothing being added or subtracted inside the absolute value bars, right? We're looking only inside here, and so that means h is equal to 0. I do see on the outside I have a -1, which that means our k value is -1. So when we put those together, that gives us our vertex of 0, -1, which I've already plotted for us. 0, -1. Remember, 0 is talking about the x-axis, and then -1 is talking about the y-axis. So make sure you understand how to plot those points. Now, remember, a stretch factor is secretly the slope. So in this case, the slope is going to be equal to 1/2. So if you're going to graph this, then we would start at the vertex, right? Just like I said, vertex. We're not starting at the origin. We're starting at the vertex. And we're going to go, this is going to be reminder. I'll remind you this. This is our rise, and this is our run. So I'm going to go up 1. So I'm going to go up 1 and to the right 2. And then I'm going to go up 1 and to the right 2. And you could keep doing that. It should look like a staircase going up and to the right. So up 1 over 2, up 1 over 2. So let's put those points in. Up 1 over 2, up 1 over 2. Now that's going in the positive direction. we still need to go in the opposite direction. So we could go up 1 over 2 to the other direction, to the left, up 1 over 2 to the left. So we're going to have points here and here. And you try to go as far as you have room on your graph. So when we actually sketch the graph, it should, let's see if I could sketch this. Whoa, this is squiggly. All right. It looks a little bit messy, but something like that. It looks a little bit crooked, but all right, so it should look something like that. You'll notice it looks wider, looks more open, but it still has a V-shaped. Orientation is still positive here. I didn't do any negative orientation graphs here, but if there was a negative orientation, the graph would look like an upside down V. All right, so I'm not going to go over any more examples. If you need to see some, one easy way is just type it into a graphing calculator and test it out. If we have time in class, we will try to play around with testing out different transformations. So that's it for now. Let me know if you have any questions, and we'll see you next time.